It's a great pleasure to welcome Estefania, Loayza, Romero here from the University of Strathclyde. Estefania has been there for a year now. Before that, she did a PhD in Heidelberg with Romero, and then did a postdoc with Benedict Worth in Munster, and was a Chapman Fellow at Imperial College. Their interests are very much aligned with the interests of people in this room and on the call. Non-smooth optimization, data assimilation, shape optimization, optimization on manifolds, and PDE-Constrained optimization. So yeah, very much looking forward to your talk.
Thank you so much. I hope you can hear me okay. Thanks a lot for the kind invitation. It's very nice to be here. So since this is the first time I'm here, I'm very excited to be here. This talk is kind of a mixture between what I have done before and what I'm doing now, also using it as a motivation, just to show an idea of what are one of my current interests, basically. So thanks again a lot for the introduction as well. There. Okay, so this is the outline of my talk. So of course I cannot talk about shape optimization or PDE-constrained shape optimization without talking about the fundamentals first. So I'm going to spend a couple, around 10 minutes or something like that, and just explain what do I mean by shape optimization, what is the difference between shape and topology optimization, what is the current usual approach, and then I will go into what my view of the problem, and it's working on shape manifolds. I'm going to introduce these two different manifolds. One is a finite dimensional one, the other one is an infinite dimensional one. And at the end, I will present some numerical results on a benchmark problem in this context, which is compliance minimization. Everything is done in 2 dimensions, but at the end of the day, this is the representation or the example of how to build an optimal shape in 2 dimensions for the moment. Okay, so when we talk about PDE-constrained shape optimization in general, in very loosely speaking, it's looking for geometries which enhance the performance of a system in a very, very general way. So here I'm just showing you some of the examples across different engineering disciplines. So you can think about optimizing, for example, an electric motor, when of course in that case the PDE will be Maxwell's equation. You can think about drag minimization, the one I'm going to present to you, compliance minimization. There is also this a little bit more inverse problems, in the sense that we want to, for example, do something inspired by impedance tomography. So we want to decide how the inclusions of certain systems are, for example, thinking about our body, how our internal organs are, just based on information that we collected by sending currents across our body, things like that, for example. And among other ones, designing pipes that at the end of the day, they will have kind of a similar flow, and many others. I like to start with this disclaimer in the sense that, at least in the community, sometimes these terms get confused, and there is this difference between what is topology and shape optimization. You're probably very familiar with this, but I still want to mention it. And topology optimization means that we are allowing our structure the creation of inclusions or holes, as you can see, for example, in the upper image. On the other hand, shape optimization, we can assume that we have a topology that we know. Most likely, we have already obtained a solution from a topology optimization problem, and now we just want to see how, or even if we can improve whatever design we got it from the topology optimization solution by running what is shape optimization. So not allowing the creation of inclusions anymore, but just changing the shapes at the end. Just to mention, this is some of the people working in either topology or shape optimization. Of course, as it's well noted, you can do shape. While you're doing topology optimization, you're also doing shape optimization, not in the other way around. But today's talk, and especially because of this view of thinking about shape manifolds, it is important that we keep at the moment the topology of the structure. Mathematically, this is the formulation of the problem. We have an objective function, which in this case we call it a shape functional. we have a set of admissible shapes, which in this moment I'm just presenting it as this very abstract object, and in a couple of slides later I will tell you what exactly do I mean with this. And finally, of course, because we're talking about PDE-constrained optimization, we have a PDE, we have this state equation, which basically represents the dynamics that are depending on the phenomena that you're using. What important thing here is that, of course, our unknown is really the domain, and it's the domain where this state equation is posed. So whenever I change my domain, I change the solution of my PDE, I change this state equation. That's exactly why I'm writing this y of omega in that case, because this is how we have to eventually know and how to measure this, how this changes, how this variable changes. And of course, that induces also a change in this objective function or shape functional, right? So with this in mind, I really like to make this connection in the sense that shape optimization, especially PDE-constrained shape optimization, they're nothing else but optimal control problems where the unknowns are these underlying geometries. And thanks to this connection, I'm going to talk later a bit on how to deal with this. But at the beginning, as I already explained, I like to talk about this set of admissible shapes. I like to say it like this. I hope this is not controversial, but in shape optimization, there is really not a consensus or which is the best shape representation that you can use. In fact, depending on which is the shape representation, you have different machinery, you have different mathematical tools to analyze or even to numerically optimize or solve this problem. So, for example, just to mention, if we think about continuous representations of shapes, you can think about phase fields, you can think about level sets, or these domain transformations, for example. You can also represent shapes in terms of splines, or you can do something like, okay, my shape is going to be, for example, an embedding of the unit circle into the plane, or I can think about diffeomorphisms representing shapes. So depending on which is or what shapes you choose, what representation you choose, you have different, let's say, mathematical framework to solve this. Of course, in the other way, we can also, or we would like at least, to have a discrete counterpart of this. How can we represent shapes in a discrete setting with a finite number of variables, for example? So one of these is called landmarks. And the other one is one of the ones I'm going to show you today is really what do we happen or how does this space of shapes behaves when you have triangular meshes, when these triangular meshes are the ones representing your shapes. And of course, if we go back to this idea that shape optimization is nothing else but optimal control problems, the first thing we would like to do is to characterize the optimality, so the optimality conditions. And for that, we need derivatives. So the question is, how do we do derivatives when we have shapes, when the shapes are unknown? So the first thing we have to settle down is the idea of what does it really mean to have a perturbed shape? Because of course, once we understand or define what is a perturbed shape, we can then think about measuring what will be the change of my shape functional when I perturb a little bit my shape. So this idea, this is one of the ways of doing it, and it's called perturbation of identity, when at the end of the day, as the name states, we just want to have a vector field, in this case V, which is telling me how I'm going to deform my mesh or how I'm going to move my mesh. So you can have different kinds, right? At the end of the day, you can have something like in the left and say, okay, for example, if my shape has two inclusions, after I apply this vector field, I also have two inclusions, meaning that I keep the topology of my structure or of my shape. But it can also happen that at the end of the day, I end up with something that has no inclusions anymore because my vector field behave in a weird way, right? Since we're doing shape optimization at the moment, we're not interested in these kind of cases, so we need to kind of restrict the kind of deformations or the kind of vector fields in order to keep the topology of my shape. And one of the ways of doing it is, in fact, by taking these deformation fields in this very particular space, so W1 infinity, and of course, asking them to be small enough. And I just want you to keep in mind for later. So for now, the idea is that now we know that we want these very particular deformation fields. We want to perturb our shapes, and this is what is going to help us to define what is called the shape derivative. So, or we say that this shape function, also the objective function of our problem, is shape differentiable if this mapping that takes the deformation field into the value of my objective, or the value of the objective function at the perturbed shape is Fréchet differentiable. So in fact, that is good because at the end, because of the Fréchet differentiability, we have this kind of expansions. And this is exactly what allows us at the end to think, if we want to solve this problem, about the descent directions. Thanks to this expansion, it's very obvious that the descent direction in this context is going to be this very particular deformation field for which the shape derivative is negative evaluated there. But of course, when you do optimization in finite dimension or in Rn, in Euclidean spaces, sometimes it's not so obvious this connection between derivative and gradient. For shape derivatives, it gets a little bit more obvious because, of course, whatever information you get from the shape derivative is not enough. You need to come up with a decent direction. And for that, I found very recently, in fact, this term called the Hilbertian extension regularization. But at the end of the day, what it means is that I want to extract the information of the shape derivative using the Riesz representation theorem by plugging in inner product there. Of course, there are many different ways. There are many different inner products that have already been tried. So, for example, you can think about H1, 0. You can think about something, a very common option in this case is the inner product associated to the variational formulation of the linear elasticity equation. So you can also plug that in. And at the end of the day, the idea is that this, what I call a gradient there, it's a shape gradient, is really the solution of this variational problem. If you think about plugging in different inner products there, that will mean that besides of solving your state equation and possibly an adjoint equation because it's a PDE-constrained problem, you also have to solve a PDE associated to this in order to find your descent direction. At the end of the day, the idea is that these descent directions are going to be vector fields that tell you how to deform your mesh in such a way that in your next step, your function will have or have been decreased, or we improve the value of our function. One important aspect is the fact that because of the Sobolev embeddings, in fact, taking an HS inner product will be the best thing to do, but not a lot of people does it. And I'm going to show you one way of doing it here. Okay, so the last important thing about shape optimization is that in general, as in optimal control problems, we also have this difference, right? So we can either do optimize and discretize or discretize and optimize. So at the end of the day, we want to end up with something. For example, for the optimize and discretize, you can choose domain transformations, phase fields. You can compute the shape derivative and just at the very end discretize. Of course, there is a second thing that we could also use one of these discrete representations of shapes, for example, the triangular meshes. And you can then see if you can get a discretized version of the shape derivative and under which conditions you will get this information. And finally, you can continue with your optimization algorithm. Just as computational aspects here is that definitely not the only method of doing it, but one of the way of doing it is by using finite elements. Why? Because at the end, in the way how I see it, is that you need exactly the same mesh or triangular decomposition of the domain to represent the changes under shape, but also to solve the PDE there. There are other ways of doing it, of course. For example, you can have one mesh to deform your shape and then initialize a new triangulation in order to solve the problem or the underlying PDE to obtain your state equation at this particular point. I think at least that the main problem about initializing a new mesh every single iteration is, of course, that when you have real big problems, initializing or getting a new mesh at each time is very computationally expensive. You need to save a lot of information. And something that, at least in my aspect, is very important is the fact that then when you change your mesh, you don't have or you lose this continuity of your objective function, which at the end you would like to have, for example, to have convergence of algorithms, or just simply to understand how you are decreasing the value of your objective function. One last thing that I wanted to mention, and it is very important, is that really there is no difference, or it doesn't matter where you start. At the end of the day, at least the computation of what is called the shape gradient, so the solution of this additional variational problem to get your deformation field or your descent direction, it's always done in the discrete setting. So we can always just get it approximated by solving the problem, right, using finite elements, for example. Okay, something very important here, and that it's a problem that has already been studied for a lot of time, is the fact that because our meshes, if we're already thinking the discrete setting, we're moving meshes, and these meshes are subject to very large deformations, right? It's almost unavoidable that eventually the mesh quality is going to reduce. And what is the problem about this is that finite elements, or how good our solutions of a PDE using finite elements is, highly depends on the quality of my meshes. If my meshes are bad, they have bad quality, they look like that, they have squeezed triangles, the solution of my PDE may not be the best one, and of course then the value of my objective function may not be the most accurate one. Thinking, in fact, whatever value you get there, you cannot trust it. And we have some numerical experiments that really show that these optimizers kind of take advantage of this situation, and they destroy or at least reduce the quality of the meshes on purpose in order to get better values of the objective function. So at the end of the day, what we would really like is to have a method in which I can take care of the quality of the meshes by, for example, posing it in a very particular space. So just a heads up, shape manifolds, in such a way that this gets taken care by in an intrinsic way, and we don't have to take care about that anymore, and we just can let the algorithms go. What is the problem right now is that, of course, our optimizers, they don't know anything about the underlying geometry of the problem. They don't know anything about the meshes. They don't know anything about that we don't trust finite elements or the solutions of a finite element when my meshes are wrong. In fact, they want to take advantage of the situation, and this is why, at least I think, the fact that using manifolds, and in particular one of them, we took care about the mesh quality by defining this shape manifold in a very particular way. So basically, this answer of how do we ensure that the shape deformations, or even the shapes, the iterates of my algorithm are geometrically valid, it's by using shape manifolds. That brings me to the next part of my talk. I want you to think about shape manifolds as this set, right? Is just a curved space, it's not a flat space, and each of these points represents a shape. So what I really say that we want to follow, or we want to intrinsically take care of the kind of shapes that we produce in our algorithm, is by moving always within this set and generating new and new meshes. So of course, what is the idea? Is that at the end of the day, when we work, or we are able to walk, let's say it, within this space, this manifold, we can assure that the shapes are going to be exactly the way we want it to be, or we choose it to be. For example, this, you can understand, or this is just a very simple illustration of how this manifold of the embeddings of the unit circle would look like. Why? Because at the end, if I would be able to move within this manifold, I know that I am always going to generate shapes that are simple closed curves, and that they will not have intersections, just by moving along this very particular set. In the same way, you can think about this, instead of being curves, being these triangulated versions of the domains, for example. I want, again, that if I move along these, I can assure that the meshes I produce are going to be exactly in the way I want it to be. That is basically the main idea. And what is another aspect here is the fact that if we let our space, our shape manifolds, to take care intrinsically of my problem, now I just get, I can just quotation marks, use these Riemannian versions of the algorithms to solve my problem. You're very probably, I'm going to use the simplest one. So for the moment, for the time being, it's just the gradient descent, the Riemannian version of the gradient descent. And I will tell you also why we are stopping there yet, so far. But let me first go to, this is just to give you an idea. So some of these shape representations are mentioned at the beginning. In fact, they are shape manifolds. It had been proved that they are manifolds. They have been endowed with very particular Riemannian metrics. Today I'm going to talk about these two. So the triangular meshes there and the space of, or the diffeomorphism group. And use that in order to make sense of what will be the different shapes for our problem. And this is exactly the version of this Riemannian gradient algorithm that we're going to use to solve our problems. There is some advantages I see about this approach, and one of them is the fact that we have, or I have highlighted in red, these two very important steps in a Riemannian gradient that you usually don't have it in a function, in a vector space or algorithm. One of these is the fact that you can choose a Riemannian metric to compute a Riemannian gradient. And if you think about this, in line 5 of the algorithm is exactly the same thing as this Hilbertian regularization extension algorithm, but this is just the definition of what a Riemannian metric is. So basically, whatever inner product I use to compute my extension of my shape derivative to compute the shape gradient can also be thought about that being a very particular Riemannian metric for a Riemannian shape manifold, for a shape manifold. But at the end of the day, the computations in the computational level, they are very similar. They're basically the same. And the second thing, it's about how do I update my shapes? Of course, when we're working on Riemannian manifolds, we cannot just have the direction and some are moving this direction straight because we're going to leave the manifold. So we have to follow geodesics. Or we have to, what I'm calling this R there is a retraction, which is going to be like an approximation of a geodesic up to the first order. But the good thing about this is that they have certain flexibility. So depending on what kind of Riemannian metric I use to compute the gradient, and depending on which kind of update of my shapes I use, I can have what we call different variants of my method. So it's exactly the same algorithm, but I have different variants of it. And in fact, what I want to show you today is that changing these metrics, it does have an impact on how my algorithm behaves, and I can get to my solution, or at least to a local solution, faster or slower than others. Another thing that, or one of the reasons I think this works is because, of course, by changing the Riemannian gradient or the Riemannian metric to compute a gradient, it does really generate different descent directions, which allows us to explore the energy landscape in a different way. And this is why we can get faster or slower somewhere. You can think about like a perturbation. So let's go a bit very fast about this set of triangular meshes first. So this is a finite dimensional manifold. And what is the idea here? So we thought about what are the kind of meshes that we need in order for our finite elements method to be well behaved and so that we can trust it. So we thought, okay, let's use conformal meshes, right? So we're not going to have hanging nodes. We are going to have the intersection of these, of the different edges or the different faces, in fact, are going to be either the empty set or an edge or a point. And it turns out that exactly the definition of what we know about conformal meshes can be expressed in the terms of simplicial complexes. In fact, this is a geometric simplicial complex. So in order to define our triangular meshes set, we use this language of simplicial complexes. So for example, the connectivity information of my mesh is going to be an abstract simplicial complex. And then the distribution of my points is going to be this, or I'm going to ensure that it's going to be a geometric simplicial complex. These sets are basically the way of describing exactly that. That at the end of the day, what you have to keep in mind is that we want meshes which have no hanging nodes, and basically they also have good quality. That's another important thing, in the sense that, for example, the ratio between the in radius and the circumradius is good. Okay, so just a very there is this other part, is the fact that at the end of the day, what we decided is to fix the connectivity of my meshes. So I'm going to have, I'm going to initialize my mesh, or like a triangulation of a certain domain, probably the initial guess of my shape, in one particular way, and I want to keep that connectivity information. And then what I'm going to do is to just ask. So, for example, these M0 and M class sets are really, what are all of the possible points or the distribution of the nodes in the space in such a way that they are, in fact, conformal meshes. So this is basically what I want to do. So my the elements of this space are really matrices, which because we're working into dimensions which are 2 times the number of nodes of my initial mesh. And then at the end of the day, one of the things is that, in fact, these sets were not connected, and we wanted them to be connected. So we wanted to be able to reach with any path to different points. And that is why we consider this path-connected component, right? So what we call this manifold of triangular meshes is, in fact, the subset of this distribution of the nodes in such a way that for a given initial reference mesh, I can attain it through continuous deformations to all of them. And in fact, of course, this we prove it's a submanifold. But we were missing something, and this is in fact the endowing it with this Riemannian structure, because so far we were not able to, or you can without the Riemannian metric you cannot compute the length of the vector fields. You cannot compute the Riemannian gradient, of course. So what we wanted is really to have a Riemannian metric, but it was not any kind of Riemannian metric. We wanted to have a metric which is complete, and complete means that all of the geodesics that are, so for all initial points in all initial tangent vectors, the geodesics always exist, or they always belong to my manifold. If you think about this very particular case of the triangular meshes, that will mean that no matter how my mesh looks, and no matter how my initial deformation field looks, if I am able to follow geodesics along this, I'm never just gonna destroy my meshes. And not only they are not gonna destroy them, but also they are gonna have good quality, because this is kind of this energy minimization property that the geodesics have. And this is exactly what we wanted to exploit. But of course, the problem, just the definition of a complete metric, is how do we construct complete metrics? And in fact, this is not very easy. You have Riemannian metrics. You can, by counterexample, prove that they are complete. That they are not complete. But really, constructing complete metrics was not super obvious. And one way that we found, in fact, is this paper from the 70s, where basically you get a recipe on how to construct complete metrics for Riemannian manifolds, as long as they are in finite dimensions. And basically, you need one base Riemannian metric that doesn't need to be complete, and another function which needs to be proper. Proper in the sense that the inverse image of compact sets is compact. So based on this, the only thing we needed to do was to find this function to be which will be proper for our particular manifold. And of course, again, coming back to the idea that we are looking into this space of triangular meshes, a proper function was exactly the one that kind of will blow up whenever I am getting to the boundary of this set. And this boundary or limit elements of the set will be when my mesh is getting, for example, squeezed and my triangles are getting very flat. But it can also be in the case when, for some reason, my mesh is bending from the outside and eventually they will overlap, right? This is also another kind of case that we would like to avoid. So in fact, the idea was to find or to construct a function phi such that these two values will be penalized, or these two cases will be penalized. I have omitted the function, but I can show you if you want later. But we were able to find this function. It has and it depends on certain parameters. But at the end of the idea, what I want you to keep in mind is that with this, we have a function for which we can run our algorithm following geodesics, and we can take many, we can basically move freely within this manifold without having to take care about the mesh quality problems, and we could get faster to one of the solutions of the problem, for example. So to fix these ideas, I want to start with this very simple example. So this it's very simple. So I have a Poisson equation as my state equation. Yes, I have this shape functional there, and one of the things is that this example was chosen in such a way that because of in the right hand side of the Poisson equation, we can infer how the solution may look like, because it's going to look like the the zero sublevel set of the function. So this is just contour plot of the right hand side. Just to give you an idea, this is how the shape derivative of this problem looks like. And as in a normal optimal control problem, we also have an adjoint equation, and in this case, it's this one here. So this is when the old results come. So this while ago, we solved this problem. What I call this the SP metric is really this computing the gradient using the linear elasticity. So this shape gradient. So we solve the linear elasticity problem. We get a deformation field, and then we follow that or negative that in order to deform our mesh. Just to give you an idea, we start, this is also the reference mesh. That's what I mean at the beginning. So we start with a circle. We initialize a mesh with that. We fix connectivity of that one, and then we're just going to deform our shapes in order to get better values of the objective function. And this is, for example, what we got. So we get like a solution we stop the algorithm at 150 iterations for this linear elasticity metric. And on the other hand, for ours, for example, use this new design complete metric that allow us to take longer step sizes by following geodesics. We get there in 15 iterations, and we even get a better value of the objective function, which was amazing. What was the problem, as you can see also there, solving geodesic equations means that we have to solve a highly nonlinear second order system of ODEs, which depends on the number of nodes that we have. This is exactly why we have such coarse meshes, because we were restricted to that. So in fact, yes, we can get there in 15 iterations, but it takes, I don't even know how many more times we need in order to get that. Since then, really my motivation or my goal has been, how can I get better results? How can I come up with algorithms or even with a variant of an algorithm that has the same kind of low iteration count, but of course that is more computationally competitive at the end of the day? How can I do that? And that is where I started working with this with my colleagues of the university in Hamburg, so the Helmut Schmidt University in Hamburg. And in this case, the idea was, okay, linear elasticity does not work so good, we already know. What other kind of meshes, of Riemannian metrics can we use? And then for this, we had to take a step back in the sense that what if we start with, again, an optimized and discretized approach? What if we use a different shape representation, in this case, the diffeomorphisms, for example, in such a way that now I can represent the shapes, the changes of my shapes through diffeomorphisms in this case. And the best thing about this is that, in fact, it has also already been well studied, the set or the family of different Riemannian metrics associated to this very particular space or shape manifold. They are called outer metrics in the sense that instead of just deforming the mesh and then using this Hilbertian extension regularization, we deform the entire ambient space. And there we induce a deformation of my shapes. How do they look like? In fact, these Riemannian metrics in this case look like this. So they have an S exponent there, which at the moment we're treating it just as a natural number, in fact, not even integer, just natural. This is a very well studied linear operator. They sometimes use, for example, Fourier transforms. If you are familiar with image registration, there is this method of large diffeomorphic deformations method of mappings, LDDMM. They use exactly this one, but that's a different problem because basically you have kind of a boundary problem while we have an initial point problem, in the sense that for the the image registration, you have a target and a template that you want to match. In the case of shape optimization, you know where you are, you know your descent direction, and you want to run geodesics along that. So that is why it's the initial value problem there. And of course, because I like to use finite elements method, and I like to use exactly the same mesh for both the deformation but also solving the PDE, I wanted to see how can I solve this problem. So the problem above in the line above, but using finite elements method and using not higher order methods, but I wanted to use exactly first order, so piecewise linear elements, also for the computation of the shape derivative. One of my first motivations there is that if you use higher order finite elements for the shape derivative, you need to, for the shape gradient, you need certain corrections on the shape derivative because basically triangles may not be mapped to triangles anymore, but they may have like curved edges and something that we didn't want. So one of the ways, or the way I found to do this, is of course at the end of the day, you can reformulate this problem as a system of different, as a system of S Poisson type problems, which can be of course approximated with piecewise linear elements, and then kind of everything just matched together. So at the end of the day, we have to solve the state equation, we have to solve the adjoint equation, and instead of just having to solve one PDE, or one more variational problem, we have to solve a system of variational problems. So yeah, you may tell me that is it really worth it? So that is why the first experiment here is that, as you can see, now my shape is not only the unit circle anymore, but I need to have this ambient space or this Holtall domain, which is large enough in such a way that I can deform my shapes. This is all of this, but on the other hand, now I'm allowed to use finer meshes. And the first thing I want to highlight here is the fact that for the same shape derivative, if we use different Riemannian metrics, so I have the linear elasticity, and then I have what will be with S equal to 1, S equal to 2, 3, and 4, the gradients look different, which kind of backs up, or yes, this idea that different descent directions may allow us to explore the energy landscape in different ways. The second thing is that, of course, we have higher, our systems now are larger. That's why I just got into 4, but in principle, this idea could work for 10, right? And that's maybe where linear algebra preconditioners will become very helpful for me. But at the moment, at least until 4, the computational burden that you have, or the computational complexity that you have by solving these linear systems, is of course a multiple of how many systems I'm using. But on the other hand, because my algorithm will get better faster there, it's kind of compensated. So one of other things is that, for example, I can even go until H2 or even H3, and just there I will have a comparable with the linear elasticity. One of the reasons is that for the linear elasticity to work, we had to solve an additional PDE for some of the Lamé parameters. This is kind of usually what the people do there. That's why you have kind of a similar value with H2 there. So let me just show you how does it work when we solve exactly the same problem, but with the new metrics. So now I can get there. Of course, I will not be able to get there in 15 iterations as before, but I can get there to even in 31 with an even better value of the objective function. I can trust even more the solutions of my finite elements because I am allowed to use finer meshes, which is also very good. And yeah, so this is kind of the motivation. So finally, to end, yes, I think I'm okay. The compliance minimization problem. This is how so compliance minimization basically means that I want, or my the equation here is the linear elasticity, and I want to minimize basically the right-hand side of the linear elasticity. But of course, if I don't have a constraint there on the volume or a penalization on the volume on my structure, the solution will just be to close in all the inclusions and have as filled as possible. So that is why I am including this value L there with the volume of the structure, and I want to see how the objective function works. How the mesh, the bridge behaves. These are just very some parameters for the problem. And as I mentioned, since we want to do shape optimization, we assume that this is the topology, the initial topology. So basically, you can think about I solve a topology optimization problem, and I got a solution which has 4 inclusions. And I just want to show you how this looks like. So again, very old, sorry, but very old, very low quality videos at this moment, some time ago. But you can see, for example, how the linear elasticity kind of gets all of these, the triangles get flattened faster than in this case. What was the drawback here is that, of course, because this was, this one, we didn't follow geodesics directly, but we used a metric to compute the gradient, and that already has an effect on the way. Another thing is that, yes, I told you that we don't want to remesh, but eventually, in some ways, in some problems, you do have to, and especially because of the nature of my problem in this case, because they get flattened and flattened, it's almost unavoidable that you will have flat triangles eventually. So we have to remesh. We wanted to remesh. So in this case, we did it just once. And what I want to show you is really the jump that you get in the objective function when you remesh. And this is exactly the things that we want to avoid. So imagine how we can say something about the convergence of my algorithm if I am initializing a new mesh every single iteration. I will lose completely this continuity. I will lose completely this information of am I decreasing or not my objective function at the end of the day, right? And this is, of course, you can see how the mesh quality was very bad, and then when you remesh it, then it was good again. But of course, we did this the exact same problem, but now with my new mesh, with my new Riemannian metrics. I'm so sorry I haven't. How do you say this? So that the videos, because they have different different number of iterations, they run in different times, so they are not synchronized. That's the word I was using. But at the end of the day, you can see that, for example, with the linear with the H4, I already need 125 iterations rather than the almost 500 that we needed with the linear elasticity. So in fact, using these metrics, it does have an impact, and the computation of them is not super difficult. So it's definitely worth trying it in case you are working with shape optimization. And this is just, again, we did have to remesh, but in this case, we have kind of like a quality measure of when to remesh. And it turns out that for most of the experiments, we just needed twice. And you can see, for example, how slow it was with the linear elasticity compared with what you can get with these new outer metrics that we just the measure of the mesh quality. It's a different measure of mesh quality. That's why it looks very different to the other problem. But yeah, I think with that, I would like to conclude my talk. If I want you to take something to home, is really that Riemannian geometry, it does provide a natural framework for shape optimization. Of course, shapes belong naturally to a manifold. If you think why is naturally, because how can you add two shapes? Or even, how can you measure if two shapes are different one from each other if you don't have a Riemannian structure behind them? You could do that. I mean, it is just natural to think about this in that way. The second thing that I want you to take home is the fact that different Riemannian metrics really impact the algorithm's behavior. So even though we were just using simple steepest descent method, we got completely different, or not completely, but different behavior. We can get to these solutions faster just by using one over other kind of metrics. The second one is that the outer metrics, they do behave better than this linear elasticity, and the computational effort is comparable to that, at least until H2. Another thing that I haven't mentioned there is that we're really answering this question of if we use HS inner product in this Hilbertian regularization extension, we can also ensure that our vector fields are in W1 infinity, so we can keep the topology of my structure. One additional thing is that, or maybe like an outlook, is the fact that these particular metrics, they have an explicit expression for the exponential, sorry, for the geodesic. And what we really like to do is to see how we can code, how can we numerically solve this geodesic equation such that we can get to a solution even faster than we have right now. Another thing that I haven't mentioned so far, or why we are not using yet higher order methods is because when you use, when you have, for example, BFGS method in Riemannian manifolds, you need something called the parallel transport, because if you remember, BFGS has the difference between two different gradients from two different iterations, but they live in the Riemannian setting, they live in different tangent spaces, so you cannot just compare them. You first need to do parallel transport, put them all together in the same tangent space in order to do that. And this is an additional process that we have to do, and this is why so far we cannot do it, but I'm also working on that. So yeah, basically that's what I say. So with that, thank you so much for your attention.
Any questions? If you go to the last slide, what's happening?
It was remesh.
You remesh. So how
at the end.
Why do you remesh at the end?
That was kind of the quality. So when we have this criteria that if the quality measure decays, then we remesh. But then also, I think in that case is because the stopping criteria, as you can see, they haven't reached a plateau. Mm-hmm. So we're just stopping when I think in the last 10 iterations, improvement has not been that much. And I think that is why, so no, I think this is why it stops kind of right after the remeshing. But yes, I could have also let them do it.
And is there a reason why all three metrics have the same behavior?
I haven't thought about that. I would say yes, but I don't know. I don't know if that's connected with, because I mean, kind of also happens with the linear elasticity that it also kind of remeshes at the end. I don't know. I haven't thought about that.
I mean, that might be a stupid question, but do you need to use compatible finite elements for, like, for example, H4? Do you need compatible, or you can use?
No. So you mean for the
higher order metrics?
No. So because of this reformulation, I'm using piecewise linear elements.
Okay.
So that's it. But in fact, so this is like I work with finite elements, but I always work with piecewise linear. So if you have a better idea, or you know different kind of elements that could work in this context for polyharmonic operators, I'm happy to hear that because I did try for a while. And
so they are not conforming elements.
No. No, yeah.
So I mean, yeah, P1 is not going to be there.
And you, question?
Yes, I was just going to ask about some of your problems clearly have physical symmetries, and here you have left-right symmetry in these things. Do you actually impose that the solution has these symmetries, or do you observe that it has these symmetries?
So yes and no. I do not impose it per se as a constraint on the optimization algorithm, but I do impose it in the sense that they are symmetric when I start. So I haven't made the experiment, but I'm very sure that if for the circles will be when you start, they break the symmetry, then you will have broken symmetry along the entire improvement, if you want to say it, algorithm, or the iterations of the algorithm. Yes. So no, we are not imposing it per se, but because of the way where I start or my initial informed topology, I do get these solutions, these symmetric solutions.
So it seems that HS, the higher S is the better, but it's computationally more expensive. Is that what I get? And so is H5 too hard for you to do, or did you try?
No, I haven't tried it, but there is one thing that I haven't mentioned, and is the fact that if I go to my metrics, they do depend in this parameter A in front, and the higher S is, the more sensitive the metric is depending on the solutions that you want. So you have to a little bit tune this parameter to get these solutions. That is true, definitely. But I haven't tried with 5 yet, but yeah, I mean, I should.
And do you have a sense of what's the slope of convergence of the as S increases? Is it not worth doing at some point? Does it level out and do you don't get any more? Or?
That will be very interesting. I don't know. I haven't studied that because I kind of just got until 4 and then but there should be, I think it should be possible to study something like that, yeah. Definitely interesting to do that, yes.
And, do you have any practical applications? So just to caveat, like I know here on site at UKRI, there are people working on shape optimization and topology optimization for putting stuff in, say, optimizing satellites. So satellites because they want to minimize the material.
Yeah. I am working right now with some colleagues from KIT in Germany, so in Karlsruhe. And the idea that we want there, they have this, I think they're called probettes or fillets, something like that, in order to test this rigidity and stiffness of certain materials. So what we want to do is, depending on the material, find what will be the best shape for these probettes, so to give you the most possible information that you can get from there. And of course, because my colleagues work in the manufacturing lab, so the idea is that we really want to print them. They have a laser to cut them and that. So that is the most applied project that I have at the moment. But yes, so you can do a lot of things.
Is whatever code you use to generate these simulations available anywhere yet?
Not yet, in fact, but yes, I can make it available. They are all done in Phoenix at the moment. That's why I haven't done it also, because it's Phoenix and not Phoenix X. And I want to first migrate it to Phoenix X before making it available. But yeah, sure, if you're interested, I can definitely share, yes.
Any more questions online? Thanks for joining everyone online.